So this is officially section 6.1 now. In the last chapter, we spent a lot of time on imaginary roots. In this chapter, we're just focusing on real roots. You can't forget about imaginary numbers altogether, but typically we're going to be seeing real number roots here. So the definition of an nth root. I kind of talked about nth roots last time. Just means like second root, third root, fifth root, 20th root, whatever. Okay? The definition of the nth root is if a to the n equals b, then a is an nth root of b. That's like the official thing. If I had 2 to the third power, what is 2 to the third power? It's 8. So 2 to the third power equals 8. So what I'm saying is, if 2 to the third power equals 8, then that number right there, that a, 2, is a third root of b, of 8, of 2, sorry. So the third root of 8 then is 2, based on this definition. We're going to be able to write that a different way. We're going to use the square root symbol a lot. It's actually not a square root symbol completely. Well, we'll talk about that in a minute. But if I'm taking the third root of something, I'm going to put a 3 there. If I'm taking the fifth root of something, then that'll be a 5 instead. If I'm taking the 20th root, that'll be a 20 sitting there. So it's not square root necessarily anymore. It's the nth root. The n is this number right here. The third root of 8 is the number that times itself 3 times gives me this number right here, and that number is 2. 2 to the third power is 8. The third root of 8 is 2. We call this the square root symbol because, in fact, if I had 2, well, let me use something different. 3 squared equals 9, then the square root of 9 is 3. Okay? There's a 2 here. We just never write it because most of the time, if we're dealing with square rooting stuff, we don't need to bother with writing the 2 that's sitting there. We'll talk more about that as the chapter goes on. But this is a square root symbol if there's no number sitting there. The reason it is because we understand that there's a 2 sitting there. Now that you understand, now that you have nth roots, a third root, a fourth root, a fifth root, the square root is what number times itself twice gives me this number right here. The third root is what number times itself 3 times gives me this number. The fourth root is what number times itself 4 times gives me that number, and so on. So the notation for an nth root is very similar to the notation for a square root. We already know that that is the radical. We already know that that is the radicand. Learned that in Algebra 1. But now we have this new guy here. The index is that number right there. Previously, until before today, the index of your radical was always 2 because you were always taking the square root of stuff when you saw that symbol. Now we're not going to be just taking the square root. So there's going to be a number sitting there. That number is the index. If you don't see that number, then what is the number? 2, because it's just a square root. Okay, now we also already kind of know this next sentence right here. If n is even, then there are 2 answers. Like when we take the square root of an equation, if I have x squared equals 25, then we take the square root of both sides, and we wind up with x equals plus or minus 5. N is even. This is a 2 sitting right here. This is a 2 sitting right here. I took the square root of a number. The index was even. If the index is even, then there are 2 answers. One's positive, one's negative. That's why we're writing the plus or minus there. The positive one is called the principal root. It's just what it's called. If I take the square root of 25 without an equation, then my answer is just 5, not plus or minus 5. So without an equation, we just keep the principal root as our answer. Square root of 25 equals 5. Okay? So, for example, 5 squared is 25, so 5 is a square root of 25. We already knew that. But 5 to the third is 125. 5 times 5 times 5. So 5 then is a cube root, or a third root of 125. I could write the third root of 125. The cube root of 125 equals 5. Yeah, this is what our work is going to look like. 5 to the fourth power is 625. So therefore, 5 is a fourth root of 625 because 5 to the fourth is 625. So I can write the fourth root of 625 is the number times itself 4 times that gives me 625, which is 5. And 5 to the fifth power is 3,125, 3125. So therefore, 5 is a fifth root of 3125. If I were to see the fifth root of 3125, then I'm looking for the number that times itself 5 times gives me 3,125. And the number that does that is 5. So that's how we will be working with nth roots. No longer just square roots, but any index up here on that radical. So right here, we have nth roots. So if I control caret, oh, we're going to go to the calculator. Control caret gets me the nth root. And now I can make like one of these problems here. I'll do the fifth root of 3125. So I'll put a 5 there, and then now I'm in my little box there, so 3125. And I should get 5 as my answer, and I do. So the fifth root of 3125 is 5. So you can use that if you're dealing with numbers. Doesn't help you very much if you're dealing with letters, though. This is your key concept right here. It's restating what I've already talked about a little bit. If a to the n equals b, with a and b real numbers and n is a positive integer, then a is an nth root of b. 2 to the third equals 8, then that means that 2 is a third root of 8. That's what you just learned, yeah. This is just coming straight out of the book, so you can see that I'm not crazy. If n is odd, so if the index is odd, if the exponent here is odd, then there is one real nth root of b, denoted in radical form as the nth root of b. And I've already showed you that. The only nth root of 0 is 0. So I could go 0, and I'm looking for the third root of 0. What is it? It's 0. Okay? So that's all that's saying right there. Now, what? Yes, there is. We'll get there. If n is even, so that was if n is odd. Now if n is even, the index is even. This number right here is an even number. And b is positive. Which number is b? The thing inside the square root symbol, right? The thing under the radical. So if we had like the fourth root of a positive number, something like that, then there are two real nth roots of b. One's positive, one's negative. The plus or minus that we were talking about that we've always been using when we take square roots. So you kind of already know this. The positive root is called the principal root. That's just what it's called. The negative root is the opposite root. The negative root is just the negative version of the principal root, the plus or minus. It's the minus. If b is negative, then there are no real nth roots because it's imaginary. Over here, that's not the case. If n is odd, then there is going to be a real root. What number times itself 3 times gives me negative 8? No. Negative 2 times negative 2 times negative 2. So we can have real answers here. Negative 2 would be the answer to that one, because negative 2 times itself 3 times gives you negative 8. That's why if n is odd, there is going to be a real root, no matter what. Doesn't matter if the number inside is negative or not. You're going to get a real root. Okay, finding all real roots. This says find the real cube roots of these three numbers. Well, all I need to do is figure out, since it says specifically to find the real cube roots, I should have 3 roots total if I take the cube root of something. Like if I take the square root of something, I get 2 roots. The cube root, I get 3 roots. The fourth root, I get 4 roots. All I want is the real cube roots of these numbers. So I'm only going to have one answer. What number times itself 3 times gives me 0.008 is the question. Is it this? Or is it this? It's the first one. It's 0.2. Why? Because 0.2 times itself gives me 0.2 times 0.2 is 0.04 times 0.2, which means I add another 0, and I get 0.008. When you multiply decimals, 0.8 times 0.8, you multiply like you normally multiply, but then you count up the number of decimal places that you had, 2, and then you move the decimal over 2 places, 0.64. Over here, 0.2 times 0.2 is 2 times 2 is 4, but then I had 2 decimal places, so I moved the decimal over 2 places. Okay, that's like, I don't know, 7th grade math, 6th grade, something like that. You just got to remember how to do it. How about negative 1,000? What number times itself 3 times gives me negative 1,000? Negative 10. So therefore, the cube root of negative 1,000 equals negative 10. And how about 1/27? Why 1/3? You plugged it in. 1/3 times 1/3 times 1/3 gives me 1/27, which is what I was looking for. So therefore, the cube root of 1/27 equals 1/3. Do not rely on your calculator to come up with these answers. Learn how to do it yourself. How about the real fourth roots of 1? What number times itself 4 times gives me 1? 1 and negative 1. There's a positive and a negative answer there. We're going to get 2 real roots with that even index. How about negative 0.0001? Why? That's right. We have an even number here, and we have a negative number here. Just like if I was asking you to take the square root of negative 0.0001, you can't do it because it's a negative number. You can't take the square root of a negative number. So the answer here is there are none. I'm asking for the real roots. None. How about the 16/81? What number times itself 4 times gives me 16/81? Why? I'm looking for a number times itself 4 times that gives me 16. What is that? And I'm looking for a number times itself 4 times that gives me 81. What is that? 3. So we get 2/3. But remember, this is an even root. So I'm actually plus or minus 2/3. Now, a lot of the time, we're just going to take the principal root, the positive case. But for now, we need to talk about both of those possible roots. How about the real fifth roots of those three numbers? Without using your calculator, come up with those three answers. So what is the real fifth root of 0? What is the real fifth root of -1? And what is the real fifth root of 32? Good. So basically what we're dealing with here is the fact that we have still this radical symbol, except now we have some number that we're putting here. That's our index. And we still have this thing inside, our radicand. It's not just a square root symbol anymore, it's a radical. It has an index on it. If this happens to have no number sitting here, then you are dealing with a square root. But if you see a 3, then you have a cube root. Or a 4, you have a fourth root, and so on. You are finding the fourth root of a number, which means what number times itself 4 times gives me this number right here. So keep that in mind. It's a different way of thinking a little bit. It's going to take some getting used to. All right. What is each real number root? We have the cube root of -8. What do we get? No. It's -2. Because -2 times itself 3 times gives me -8. How about the fourth root of -1? Yeah, we're looking for real roots here. There actually are 4 roots, but all of them are imaginary. So none here. The answer would just be none. Because I'm saying, what are the real roots? There are none. How about the one below that, the cube root of -27? Good, it's -3. And how about this? What is this one saying? The square root of 0.04. What number times itself gives me 0.04? 0.2. What's the next one saying? Okay, so the square root of -2 squared. What should I do? Close. The answer is what? Plus or minus 2. If I square inside first, I get what? 4. And now I take the square root of 4 and I get plus or minus 2.
So where is the radical
They're one and the same. It's a good question, and we'll get to it later. How about the last one? None. Good. So squaring does undo square rooting. So it's tempting here to say just -2. But the negative root is not the principal root. There are 2 roots when you have an even index here. So we have to say plus or minus. Which side? Yeah?
Like, why isn't that an exponent?
Here?
Yeah.
That's an index. It's understood that if you don't see a number here, the number is actually 2. All along, when you've been using the square root, square as an exponent is the exponent of 2. So all along, when you see this symbol right here, you've been using an index of 2 on this radical. We just don't see it because we use it so often that that's one of those things that we don't bother writing. It's kind of like if I have a number like -2, there is an exponent on that number. What is it? 1. I'm not going to sit there and write an exponent of 1 on every single number that I write. It's just something that we don't do. Kind of like we don't write the 1 in front of a variable, or the 1 in front of parentheses, or the 1 that comes after a negative sign. There's no need because we understand that it's there. With these guys, this is another case where we understand that there actually is a 2 sitting on each of these as an index. Okay? Nth roots of nth powers. This one is kind of an important one. It's a big deal. For any real number a, the nth root of a to the n. We kind of just saw that on that last problem with the square root of negative 2 squared. The nth root and the exponent of n do cancel each other out. I hate using that word cancel, but that's kind of what they do, and I know that's how you guys think of it. So, if if n is odd, so they will wipe each other out if this index right here is odd and this exponent is the same. You'll just get a. But if this is even and this is the same number, so you're dealing with like the square root of something being squared, then you wind up with the absolute value of the number that you saw. Kind of like what we just saw with that negative 2 being squared. You wind up with 4. Take the square root of 4 to get plus or minus 2. Okay? So we're going to have to include absolute value symbols around this when you have this case. So this is true if the resulting power on A on n is odd. It's a weird one. So it's going to take some practice. We'll have to remember that it's there. Basically, if you're taking the odd root of something, you don't got to worry about this rule at all. You just take the odd root. It's fine. But if you're taking the even root of something, and what you're taking the even root of has an even power on it, and you wind up with an odd power as your answer, then you have to include absolute value symbols around that part. Just that part, not the whole thing. You'll see it. There's an example here pretty soon. So, to simplify nth roots, try to match the power under the radical with n. That's this number right here. So we're trying to match the exponents underneath with that 5. Watch for the need for absolute value. That's this rule right here. And when it happens, I'll point it out. It'll be a little bit more clear. So what I'm trying to do is I'm trying to figure out what times itself 5 times gives me 243. Or what's the biggest perfect fifth power that's a factor of 243? Is there a number of times itself 5 times that gives me 243? No? Let's be sure about that. Oh, really? It's not a factor of 5, though. It's a number of times itself 5 times that gives me 243. It's 3. So what I'm going to do is I'm going to write the fifth root of 3 times itself 5 times gives me 243. So I'm going to write 3 to the 5th power. Then what times itself 5 times gives me a to the 20th? A to the 4th. Good. Because a to the 4th to the 5th, when I have powers to powers, I multiply my exponents together. A to the 4th to the 5th would become a to the 20th. And now I've written a to the 20th as something to the 5th power. How about b to the 25th? What could I write that as? b to the 5th to the 5th. Think of it as a game. Trying to match exponents and indexes. Now, the reason that I'm doing that is because now I can take the 5th root of 3 to the 5th. Based on this rule right here, what do I get if I take the 5th root of 3 to the 5th? I get 3. What do I get if I take the 5th root of a to the 4th to the 5th? A to the 4th. What do I get if I take the 5th root of b to the 5th to the 5th? B to the 5th. And that's my answer. Yes. I want you to go through those steps and convert your exponents into powers to powers and make this outer exponent match the index here. If you can do that, then you can take the 5th root of things very easily. Calculators will not allow you to do this. So you have to know how to do this by hand. Yeah. Mm-hmm. Right. Right. Yes, but the original index here is odd. For any real number that has this situation here, if it's going to be a if n is odd. The index was odd, so we're on this line right here. Our a in this case is 3. Our a in this case is a to the 4th. Our a in this case is b to the 5th. Because I'm taking the odd root of that odd power, I have that case right there, and I'm just left with that number. Okay? Try not to focus too much on this and try to understand what it is that happened from here to here. The 5th root of the 5th power goes away. Okay? Kind of like if I take the square root of something squared, they go away, same thing. On this one, in fact, what are we doing? This is the square root of something. If you want to remind yourself that I need to have a 2 there, then fine. You don't have to do that. But what am I trying to convert everything into? Things that are squared. Yeah. So I need to find what squared gives me 16. 4 squared gives me 16. So I'm going to write the square root of 4 squared. What squared gives me x to the 4th? X squared squared. And what squared gives me y to the 8th? Tricky one. Y to the 4th squared. Remember that powers to powers multiply. So we're trying to come up with numbers that multiply with a 2 sitting here. 2 times what gives me 8? Well, that's got to be 4. Now I can take the square root of all these things that are being squared. What is the square root of 4 squared? 4. What is the square root of x squared squared? And what is the square root of y to the 4th squared? Y to the 4th. Okay, so now let's take a look at this rule. It was the even root of an even power. Even root of an even power. We wound up with an odd exponent here, 4 to the 1st. But we wrote 4. If I put absolute value brackets on 4, am I going to change anything? No, so I don't need absolute value here, but that would be a case where I would need absolute value. X squared, we wound up with an even power here. So this little clause right here is not in effect. I don't need absolute value here. And if you think about it, even if this number in x was negative, when I square it, it winds up positive anyway. Same thing is true with y to the 4th. If I raise a negative number to an even power, then it winds up positive. In all of these cases, I don't need absolute value. If I had a 3 here, though, I would have to put absolute value on that. Okay? So in this case, that's the answer. We have 3 more problems, and then we're done with the section. The square root of 16 to the x to the 8th power. What do I need to do? Not dividing anything. It's a square root, so I'm rewriting everything as things squared. So this will be good. Okay. Now what happens? Square root of 4 squared is good. And then, okay, now that was an even root of even powers. Did I wind up with any odd powers? No, so I don't need to worry about absolute value. But 4 is already positive, so I don't have to include absolute value there. Okay, so this time, what do we need? Yeah, we have an index of 3 here, so that means I'm trying to turn everything into a third power. So a to the 6th, written as a third power, would be what? Good. A squared to the 3rd. And the next one? To the 3rd. Good. So now everything is written in terms of a third power, so I can take the cube root of everything. What do I get? Okay. And do I need to worry about absolute value here at all? Why not? The index here is odd, so there's no need to worry about absolute value. And the last one. Rewrite it. 4th root of what? X to the 3rd to the 4th. Y to the 4th to the 4th. And what do we get? Good. This was an even root of an even power, and we wound up with an odd power. I have to include absolute value around that x to the third. What else do we get? Y to the fourth. Even root of an even power, we wound up even power, so we don't need an absolute value around that. I include absolute value on this, though, to follow that rule. Okay? Even root of an even power winds up even, don't need absolute value. Even root of an even power winds up odd power, I need absolute value. Okay? And it's only around the part that had that case happen to it. That's how you follow that rule. Yeah, if there was if we wound up with like a 2 here or something, I don't need the absolute value on that. It's only on this case right here. And that does it for the section.